In question 6, a particle P moves with constant acceleration of I minus 2j. We know that at time t is 0, we are at point A with position vector 2, 5, moving with velocity u meters per second. And at time t is 3 seconds, we are at the point with position vector minus 2.5 I plus 8j, and we need to find u. Well, let's remind ourselves that the position vector is given by r naught plus ut plus a half at squared, where r naught is the initial position vector, u is the initial velocity, and a is the acceleration. We know that when t is 3, we are at point minus 2.5 I plus 8j. So this means that minus 2.5 I plus 8j is equal to the initial position vector, which is given to be 2i plus 5j, plus 3 times u, because u is the unknown, plus a half times the acceleration, which is given to be I minus 2j times 3 squared. So this leads to minus 2.5 I plus 8j is equal to 2i plus 5j plus 3u plus 4.5 I minus 9j. I will simplify the right hand side, so I've got minus 2.5 I plus 8j is equal to 6.5 I minus 4j plus 3u. I will collect the i's and the j's on the left hand side, leading to minus 9i plus 12j is equal to 3u. So dividing throughout by 3 takes me to minus 3i plus 4j, that's meters per second, which is the initial velocity u. In question 7, we've got a particle P moving under the action of a single force such that the velocity is given by this expression here. We are told that the mass of P is 0.5 kilograms, and we need to find the time at which the magnitude of the force acting on P is 6.5 newtons, where we know that acceleration is the rate of change of velocity with respect to time, so it's dv dt. So I will take the expression for the velocity given here and differentiate with respect to t. So it's essentially two derivatives, the derivative of the I component, the derivative of the j component. The derivative of t squared minus 3t is simply 2t minus 3. So that's the component of the acceleration in the I direction minus 12j. Now we know that the force is simply mass times acceleration. So in our case, it's going to be 0.5 times 2t minus 3i minus 12j, and I can now proceed in simplifying this. This leads to t minus 1.5i minus 6j. Well, we have been told that the magnitude of the force is 6.5 newtons, and this can be found by taking the I component and squaring it, plus the j component and squaring that, all of its square root. So this is giving me an answer of 6.5. So I can remove the square root by squaring the right hand side, leading to t minus 1.5 squared plus 6 squared is equal to 6.5 squared. So we've got that t minus 1.5 squared is equal to 6.25, and therefore t minus 1.5 is plus minus the square root of 6.25, which leads of course to t minus 1.5 being equal to plus minus 2.5. So either t minus 1.5 is 2.5 or t minus 1.5 is equal to minus 2.5. So from the left hand side we get that t is 4, and from the right hand side we get that t is minus 1. Obviously a negative value for the time t is rejected, so I have to reject this. I say it's not valid, and therefore my final answer for this question is 4 seconds. Remember to include the units in your answer. In question 8, a small box of mass 3 kilograms is moving on a rough plane inclined at an angle of 20 degrees to the horizontal. The rope makes an angle of 30 degrees with the plane as shown in the figure here, and we know that the tension in the rope is 25 newtons. The coefficient of friction between the box and the plane is 0.3, and we need to find the acceleration of the box. So let me start by adding the tension on the string. It's 25 newtons. I will be adding the forces so I have a complete picture of what's happening here. I'll start with the weight, which is 3g, and I will resolve this in a perpendicular direction. The angle here is 20 degrees also. So this will give me 3g cos 20. Well, we have been told that the box is moving up the plane, so it's accelerating upwards. So this is the acceleration over here with the double arrow. And I will be resolving the tension in the string along the plane and perpendicular to the plane. So this is giving me 25 cos 30 along the plane and pointing upwards. Whereas in the vertical direction, I've got the 25 sine 30, which is the perpendicular component of the tension, plus the reaction force. And then we also have the component of the weight along the plane together with the friction, which is acting down the plane to oppose motion. So now I have a complete picture of all the forces acting in this situation here. So we will start by considering the perpendicular forces. So we have that 25 sine 30 plus the reaction R must be equal to 3g cos 20. So this means that R must be 3g cos 20 minus 25 sine 30. I'm not going to use my calculator yet. I will keep it as exact. Now, because the box is moving, the friction has attained its maximum value. So we say that F is equal to F max. This is given by mu R, which in our case will be 0.3, the value of mu given the question, times 3g cos 20 minus 25 sine 30, which is the value of R we just found. I will now turn my attention to the forces acting along the plane. Now, because the box is moving up the plane, then we've got a resultant up the plane. So I'll be doing forces acting up the plane, which is 25 cos 30, minus forces acting down the plane, which is 3g sine 20 plus F, is equal to mass, which is 3 times acceleration. So 25 cos 30 minus 3g sine 20 minus F, which was found to be 0.3 times 3g cos 20 minus 25 sine 30, and all of it divided by 3 will give me the acceleration. Plug everything on the calculator, we get a value for A of 2.35, and that's meters per square second. In part B, we are asked to suggest an improvement to the model that will make it more realistic, and there are quite a few things we could mention here. One of them is taking into account air resistance. Another thing would be taking into account the dimensions of the box, because modeling the box as a particle means that the dimensions are neglected. Or we could also say that we could take into account the weight of the rope, which we have modeled this as having negligible mass, as being light. In part C, we are told that the rope breaks and the box slows down and comes to rest. We need to show that after the box comes to rest, it will immediately start to move down the plane. So I need to revisit my diagram. There is no string here, so there is no tension. I will resolve my forces once more, starting with the weight of 3g, which is resolved as 3g cos 20. We've got the reaction R. We've got the component down the plane of the weight, which is 3g sine 20. And obviously there is a tendency for the box to go down, so we've got a frictional force opposing this motion. So we can immediately equate the forces acting perpendicular to the plane, and this gives us that R is 3g cos 20. Now we do not know whether the frictional force F here has attained its maximum value, so I will start by calculating F max, which is given by mu R. In our case, this will be 0.3 times 3g cos 20, which gives an answer of 8.288 newtons. Now the component acting down the plane, 3g sine 20, I will put this on the calculator. It gives an answer of 10.055 newtons. Therefore, we say that since F max is less than 3g sine 20, there will be a resultant force down the plane. So essentially, the maximum frictional force available will not be enough to stop the box sliding down the plane, and therefore we will see it start moving down the plane. In question 9, we've got the beam AB of mass 20 kilograms and length 3 meters smoothly hinged to the vertical wall at one end A. It's being held in equilibrium in a horizontal position as shown in the diagram here. We've got the rope here fixed to a point C on the wall vertically above A, such that the angle with the wall is 30 degrees. We're modeling the beam as a uniform rod, which means that the center of mass is acting at the midpoint of AB, and we're modeling the rope as being a light inextensible string, and we need to use this model to find the tension in the rope. So I will start by adding some of the forces acting here. I will start with the weight. The weight is 20g. It's acting at a distance of 1.5 meters because, as we already said, the beam is modeled as being uniform. And then looking at the tension here, I will resolve this into a vertical component of t cos 30 and a horizontal component pointing towards the of magnitude t sine 30. The distance at which this is acting is simply given by 1 sine 30. So I can now take moments about A. We've got the clockwise moments are acting at a distance of 1.5 and have a magnitude of 20g. So it's essentially the weight of the beam. And this is equal to the anti-clockwise moments, which is the t cos 30 acting at a distance of 1 sine 30. So this is equal to 1 sine 30 times t cos 30. This means that we get 30g on the left hand side over sine 30 cos 30 is equal to t. Plug this on the calculator and we get t to be 679 newtons. In part B, we're asked to find the direction of the force exerted by the wall on the beam at A, and in order to do that, I'll go back to my diagram here and add the forces acting at A. Obviously, there must be a horizontal component pointing to the right to essentially balance off the t sine 30, so I'll call this Rx. It's the reaction at A acting in the horizontal direction. And there is also a vertical component pointing downwards, which I will call Ry. So looking at the horizontal forces, we can say that Rx is equal to t sine 30. We have already found t to be 679. So this gives me 339.48 newtons. Looking at the vertical components, the forces acting upwards are t cos 30, and it must be equal to the forces acting downwards, which is Ry plus 20g. So we've got t cos 30 minus 20g is equal to Ry, and you put this on the calculator, we get that Ry is 392 newtons. We can therefore proceed by revisiting the diagram. I've got it drawn here again. We have found the horizontal component to be 339.48. We've got the vertical downward component being 392. So we can see the resultant by completing the rectangle being acting in that direction to the right and down at an angle of theta below the horizontal. So we can see that this part here is 392. So obviously this leads to tan theta being equal to 392 over 339.48 . So we can say that theta can be found by doing shift tan of 392 over 339.48 . This gives an answer of 49.1 degrees. Therefore, we conclude that the force is acting at 49.1 degrees below the horizontal and away from the wall. Please be careful. You will get the final mark only if you mention both the below the horizontal and the away from the wall, because we need to fully specify the direction of the force. In part C, we are told that if the rope was not modeled as being light, state how this would affect the tension in the rope, explaining your answer carefully. So up to now, we've been modeling the rope as being light, which essentially means we are neglecting its mass. However, in reality, it has some non-negligible mass. So if it was indeed not being modeled as being light, then the rope would have to support its own weight in addition to the weight of the rod, and hence the tension would increase for the rod to be kept in equilibrium. And we are then told that the rope is now removed and it's being replaced by a longer one, still attached to the wall at C, but is now attached to the beam at G, where G is the midpoint of AB. So at the point at which the weight of the beam is acting, the beam AB remains in equilibrium, and we need to show that the force exerted by the wall on the beam at A now acts horizontally. So let's look at the situation. This is what we have here. We still have the weight of 20G acting at a distance of 1.5 meters from A. We've got the tension here. We've got the reactions in the horizontal Rx at A and in the vertical Ry. And we will be taking moments about G. So if I take moments about G, then I've got simply that 1.5 times Ry is the anti-clockwise moment, so 1.5 Ry, and we have no clockwise moment, so that's 0, which simply means that Ry is 0. Notice that by taking moments about G, I have completely eliminated the need to consider the weight of 20G, the tension, and the component Rx, because the only force that is acting is the Ry, which has led to me concluding that the reaction at Y is 0, which simply means that there is no vertical component, and therefore the force exerted by the wall on the beam at A now acts horizontally as required. Question 10 is on projectiles. We've got a tennis player serving a ball to pass over the net. The ball is given an initial velocity of 45 meters per second in a direction of 10 degrees below the horizontal, and the ball is struck at point O, 3.5 meters vertically above point A, as shown here. The bottom of the net is at point B, 12 meters from A, and the height of the net is a meter. Everything is shown on the diagram here. We need to use this model to find in centimeters to 2SF the distance between the ball and the top of the net as the ball passes over the net. So let me annotate my diagram. We've got the initial velocity of 45 meters per second, 10 degrees below the horizontal. I resolve this into a horizontal and vertical direction. So the horizontal is the 45 cos 10 and the vertical is 45 sine 10 and acting downwards. Now we are passing over the net at a point here, so I will call the distance between O and this point to be H as shown here. And I will proceed with Sauvat equations in the horizontal and vertical directions to determine the distance between the ball and the top of the net, which is this distance here, over here. So once we find H, it's going to be 3.5 minus the H minus the 1. That will give me the distance above the net. Starting with the component of the velocity in the horizontal direction, which I will call Ux, this is 45 cos 10, and we know that there is no acceleration in the horizontal direction, so the acceleration in the x direction is 0, whereas the velocity in the y direction is 45 sine 10, and the acceleration in the vertical is g. Now we know that s is ut plus a half at squared, so in the horizontal direction we've covered a distance of 12 meters, so 12 is equal to 45 cos 10 times t, leading to 12 over 45 cos 10 to be the value for t, whereas in the vertical direction the displacement is h, and this is equal to 45 sine 10 times t plus a half times the acceleration of g times t squared. So we've got that h is equal to 45 sine 10 times t, which is 12 over 45 cos 10. We found t from the Sauvat in the x direction, plus a half times g times 12 over 45 cos 10 squared. So I can plug everything on the calculator. I get h to be 2.4752 ... And therefore we conclude that the distance between the ball and the top of the net is gonna be 3.5 minus 1 minus the 2.4752 ... This is in meters. It gives me an answer of 0.024798 ... meters. We've been asked to give our answers in centimeters to 2SF, so this is 2.5 centimeters. In part B, we need to find to two significant figures the speed of the ball as it passes over the net. So once more, let me write down that my u in the horizontal direction is 45 cos 10, and the acceleration in the horizontal is 0, whereas in the vertical it's 45 sine 10 and g respectively, so the acceleration is g. We have already established that t is 12 over 45 cos 10, and we know that v is u plus at. So in the horizontal direction, the component of the velocity remains the same. So Vx is ux, which is 45 cos 10, which is, if we put it on the calculator, 44.3163 ... Whereas in the vertical direction, the component of the velocity is given by 45 sine 10 plus g times t, which is 12 over 45 cos 10. If we plug this on the calculator, we get the vertical component of the velocity to be 10.4678 ... Remember, we're trying to find the speed, which is the magnitude of the velocity. So this will be 44.3163 ... squared plus 10.4678 ... squared, and all square root, which gives an answer of 46 meters per second, correct to two significant figures. And finally, we need to state two limitations of the model that could affect the reliability of our answer. So first of all, we are modeling the ball as a particle, so we are completely neglecting its dimensions. So dimensions of the ball have not been accounted for, and also we have ignored the air resistance. These are the two things you could say, two limitations for the model.